So yeah, you're talking about the 12 gone, okay? So you'll get symmetry operations if you rotate by these angles. So your A, remember A is the rotation symmetry operation. You're just rotating A each time. So if you rotate 12 times by this angle, you will eventually get back to where you started, to E. Right? So that's one of your angles that you could rotate at. This is another one. So for this one, you'd be rotating every pi over 4. What is that? 45 degrees. Was that 8 rotations? Yeah. Okay. Pi over 3, so that would be 6 rotations to take you back. 2 pi over 3 is another one. So if you so you only have 3 rotations to take you back, so that's like 120 degrees. Pi, just 180 degrees, so just 2 rotations will take you back to E and do nothing. So there's your unit member. Okay, so 1, 2, 3, 4, 5, 6. So you have 6 rotation operations, and they each give you a subgroup. Right? And the subgroup is with A is your generator. Right? Remember, A is the operation that rotates you by this amount, this angle. So each of these are cyclic groups. Well, yeah, they're subgroups of this. Well, this. Okay. So for D12, we have 28 dihedral type subgroups. I don't know if you can see that SG, just subgroup. And we have 6 rotation type, staying in the same plane, not flipping to the other side, just the one-sided type rotations. Right? So 6 of those. So 34 total. Right? Now your B, remember, is any one of the flip operations. And if you have 12 gone, there will be 12 of those. Right? Alright. Okay. So let's talk about the generators. So for the B will be any one of your 12 flippers, the various ways you can do that. So that's not too difficult. Now A, A is one of these. It'll be one of these rotations in the same plane, the same face, by these angles, and you've got 6 cases. So if you're rotating by this much, you'll have 12. You'll need 12 rotations to get back to the unit, and this cyclic group with this rotation angle is isomorphic. Here's the isomorphic sign here. It's isomorphic to Z12. Right? If you want to show that. And the 12 here corresponds to the number of rotations you need. Right? And similarly for the rest. So if your angle's now pi over 3, if you're rotating pi over 3 each time, you'll need 6 rotations to take you back to the unit, 360 degrees or 2 pi radians. So if 6 times this gives you 2 pi, 12 times this gives you 2 pi, and so on, right? And the cyclic group you get with A being that is isomorphic to Z6, right? And that's for your hexagons. That's for the whole thing, the duodecagon, the 12 gone. Right? Now, if your angle of rotation is pi over 4, you'll need 8 rotations. 8 times that is 2 pi. Right? You need 8 rotations to take you back to the unit, and and the cyclic group with your generator A, that's isomorphic to Z4, right? And that with that rotation, that's like your square. Could be your square. It's like rotating a square to get symmetries. Now for this one, that would be like rotating the symmetry operations of your triangle with that angle. So you'll need 3 rotations to take you back to the unit, and the cyclic group with A as the generator is isomorphic to Z3. And if you rotate pi, that'll take you 2 rotations, so you're just rotating 180 degrees, or pi radians, okay? So that would be isomorphic to Z2, I suppose, okay? And don't rotate at all, okay? So, right? Now, Barnard, the author, he's in a bit of a catch-22 situation, in the sense that to explain the subgroups of D of n, he needs Lagrange's theorem, which says, and we'll do it next lecture. Lagrange's theorem says that the size, or the order, of a subgroup divides into the order of its group, of its parent group. In other words, the subgroup size is a factor of the size of the group. Now you're sensing that already. Look, these numbers here, they're all factors of 12, right? They're all factors of 12. Now you may ask, okay, so you've mentioned these subgroups, but how do you know? Like, in a sense, we're talking like a classification here. We're listing all possible subgroups of D12. So the obvious question probably comes to your mind, okay, so you've made this list, how do I know, you're asking, how do you know that the list is complete? There may be others, right, of different orders here, like different numbers. Well, from next chapter, from when we talk about Lagrange's theorem, which is one of the most famous theorems in the whole of finite group theory, because it's so incredibly useful. From that, you can show that if given the order of your group, if a particular integer is not a factor of that group, then there is no subgroup of that size. Like, I'll give you a concrete example. Say, what about D7? Now, there's 6 and 4, one on D7. Well, because 7 is not a factor of 12, right? And neither is 9. I mean, what about 11 and 10 and 9 and 8 and 7? Well, none of them are factors of 12. 6 is okay, 5's not, so there's no mention of 5. 4's okay, 3's okay, 2's okay, 1's okay. They're all factors. But the reason why there aren't any more is due to Lagrange's theorem. Okay? Now the catch-22 is, which do you present first? Do you talk about Lagrange's theorem, or do you talk about dihedral groups? Well, he uses dihedral groups to explain Lagrange's theorem, because it's easily done using dihedral groups. So he's sort of stuck, right? Does he explain story 1 first in order to explain story 2? But he needs story 2 to explain story 1, so he's stuck. And you have to book chapters are sequential, right? You have to present one and then the next one. So which order you do? And he chose to talk about dihedral first. All right. Okay. So so taking the result of the next chapter, Lagrange's theorem, which is pretty easy to state, proving it is a bit harder. You need quite a bit of theory. Anyway, but we can use the result. So now we've talked a bit about the duodecagon, the 12-gon. Let's try to generalize now to general n. Now here's where it gets quite detailed, and it may not be at all obvious to you. You would really need to study this quite carefully, I think, to get a really intuitive feel of it. But I'll